Okay guys, here's a video I'd like to share with you about how you could use a single vision camera to figure out distance to an object. There are other tricks obviously out there using stereo vision, but this method is very simple using single vision. Of course, the method I'm going to show you only applies to static objects, but I'm sure you could come up with tricks to apply the same method for moving objects. But anyways, let's have a go through and see how simple this is. So this drawing here is a representative of a very simple scenario of an object next to a camera. So the camera starts from here to that side. So you've got a very simple setup for a camera. You've got a lens and a CMOS sensor, and an object at original location here with a height, say h. The lens is about a distance f away from the CMOS chip. This would be the focal point to focus the image on the CMOS sensor. So the trick is really to move the object a distance m, and to figure out what the how much the image has grown on the CMOS area. So if this was the original position of the object, then we would see a reflection with a height here of a. If we then bring the object close or move it closer to the lens, now you could apply the same algorithm to a distance greater. So if you moved this way, okay, if you increase the distance between the object and the lens, you could move this way. But let's do it this way. So the object moves closer to the lens. So that what would happen then is the image grows to a bigger size, and then you could assign a length, a new height of b. I was thinking of this idea when about 6 years ago, when I was thinking about building a robot that would be able to judge distance between object and itself, but it never really proceeded further because I lacked the algorithm to do various image processing things like edge tracking, which is vital for this sort of algorithm. Anyways, let's run through the algorithm. So using very simple high school trigonometry, you can pretty much see what's happening here. So the angle created between the height and the adjacent length, which is the actual distance from the lens to the object, d, is tan theta 1, and you can easily see that tan theta 1 is also equal to a over f. F is again the focal distance. Now you'll see how that's not really important in the later part of the equation. So you can, in a similar way, you can generate the second equation, which is for the grown image on the CMOS sensor. So you have the new height b divided by f equal to tan theta 2, which is the new angle, and that is also equal to the new the same object which has got the same height, but it's moved a distance m. Therefore the new adjacent side length is d minus m. Now you can use the same equation, these two equations, and divide them. And see, look what happens when you divide equation 1 with equation 2. So the f disappears, and so you go this times by the reciprocal of this one. So then you keep simplifying it. You come up with 1 minus m over d. Now notice, if you've got a camera sensor, you would know what the length of A is, what the length of B is, because you can measure pixel distances, and you would know how much you've moved closer to the object. So you can either move the object close to the lens, or you can move the camera closer to the object. It's the same thing. So therefore you know the distance m. What you don't know is d, and you're trying to find that out. So if you make that the subject by manipulating the equation, you will see this equation, which basically says d equals m over 1 minus a over b. So what this basically means is all you have to do is move the camera a small distance and find out the growth rate of the image on the CMOS sensor, which is over here, and then you have the original distance of the object. And this is very straightforward. There's hardly any processing to be done if you were to run this algorithm on an image conceptually. But of course, to be able to figure out the height of an object or the size of an object, you need to count the pixel distance, and this is where the edge tracking comes in handy. So you need to have some algorithm to find out the edges of an object. So if you had this, if this was your camera view and you had an object on the first snap, you need to be able to figure out the, let's say, so in this case we will have the perimeter length. So notice how this applies to length, not area. So once you have the perimeter length on the first snap, you then take another second snap, and hopefully the object grows as you move closer. So once you have a bigger perimeter, you can then basically divide the first perimeter, which was your A, and divide the second perimeter, which is your B, and run through this calculation. You will come up with the distance B, which is the original distance between the object and the lens. And if you mount a camera on a servo, I can see this being a neat little trick where you could move the camera very quickly at a certain distance, take image, process it, and move back the camera to the original distance and figure out the the original position, and figure out the original distance between the original position of the camera and the original position of the object. Another situation where you would may want to use this sort of trick is when you have two cameras, for example. So you have an object at some distance from, let's say, a camera, and you could have a second camera, presumably very close to the second camera, to the first camera, but this second camera is at a distance back. Actually, this would have to be at a distance forward from the first camera. So you would go a second camera sitting a little bit ahead of the first camera. So this is your first, this is your second. So you could basically take an image from this camera. You could have a CMOS processing, a microcontroller processing the images. So you could take a snap with this camera first, and at the very same instant you could take a snap with this camera, compare it within your microcontroller, process it using edge tracking algorithm, and basically figure out the growth rate between the two, and figure out the A over B. And you do 1 minus A, and then divided by the distance, how far, what the difference is between the first camera here and that camera there. So that would be your M, and that'll instantaneously give you the value D, which is this length here from the first camera between the object. So this is a very neat little trick you could apply.